Welcome. In this video, we're going to be looking at maximum likelihood estimation for the p parameter in the geometric distribution. So to begin with, suppose we have a sequence of independent and identically distributed random variables, x1, x2, all the way up to xn. We're going to say that they are IID geometric. So they all have a geometric distribution with parameter p. And of course, those these are n observations from a sample. So the probability mass function, I'll shorten that to the PMF, the probability mass function of xi is, well, we can write it as p xi given the parameter p is equal to 1 minus px to the power of xi p, where xi is an element of 0, 1, 2. So in this case, I'm using the definition of the number of failures, xi, until the first success. That in this case, I'm using that definition for the geometric distribution. There are a number of other definitions we could use, like the number of trials until the first success. But in this case, I'm going to say it's the number of failures, xi, until the first success. And because we have that, it means that our xi can actually take a value of 0. We could theoretically have 0 failures and the success on the first try. Now that we've established the PMF, we're going to look at the likelihood function. So the likelihood function is given by, okay, let's take a look. So it would be L of P. Remember, the likelihood function is itself the joint probability or joint mass function, or the joint distribution of x1, x2 all the way to xn. And because x1, x2, and xn are independent, we can say that it is the product of their respective marginals. And then we're going to substitute our expression for those marginal distributions, which you've already got up here, or that we specifically set up here. This was our formula, 1 minus p xi p. Now I'm going to split that up, so I'm going to say that's I equals 1 to n, 1 minus p to the xi times I equals 1 to n of p here. Now, given the power laws, remember when we have a product of a series of powers or a series of base to the power of something where the bases are all the same, we can use the power laws to say that it's actually the sum of all the powers. So this expression here becomes 1 minus p to the sum of I equals 1 to n of xi. And in this expression here, we can rewrite this quite simply as, well, here we notice we're multiplying p by itself n times. So this can be simply written as p to the n. And this is in fact our expression for the likelihood function. So now we're going to find the log likelihood function. So the log likelihood function is, so by definition we'll call it lowercase l of p is equal to log L of p, and now we're going to take log of, so it's log of the likelihood function, so I'm going to get our expression here, copy that expression down below here, and then just close that bracket off. Now, we know what we're going to focus on our logarithmic laws here. Remember, a log of a product, so here we have a product of this expression here times this expression here. So log of a product is sum of logs. So the first step in simplification becomes log of 1 minus p to the power of I equals 1 to n xi. And we can then write plus log p to the power of n here. And now all we have to do, there's only one extra step of working, and that's to recognize that here, when we have one further logarithmic law, I should say, is that when we have a power or a base to a power, what we can do is we can take that power down the front. And that's precisely what I'm going to do. So I'm going to take I equals 1 to n xi down the front, and I'm just going to put brackets around it to make that more clear. And then times log 1 minus p, so it's still log of the base inside. And quite similarly, we're going to do the same thing here. So we're going to take this n, we notice the n, and that n is going to come out the front. So plus n log p. And of course, in case I forgot to mention, this log of course refers to log base e by default. So now that we've found the log likelihood function, our goal will be to differentiate this with respect to the parameter p, set that derivative equal to 0 to find the MLE. And then what we're also going to do is we're going to need to find the second derivative with respect to p, and then we're going to use that second derivative to in fact show that this is the function attains a maximum at that value that we solved previously. So first of all, what we're going to do is we're going to find the first and second derivative. So differentiating with respect to p gives. Alright, so we're going to differentiate dl of p, the log likelihood function, with respect to p. Alrighty. Let's see what we have. So here we're going to just focus our attention here. So this is a constant with respect to p, so we don't have to worry about that one too much. But this, of course, is a function of p. And how do we differentiate a log function? Well, it's 1 over the inner function, so it's 1 over 1 minus p. But then don't forget, we also have to multiply this by the derivative of the inner function. In this case, the derivative of the inner function is -1. And then, of course, we still multiply by the constant. And in this case, that sum of xi's is the constant. And this one is a little bit simpler. How do we differentiate log of p? Again, log of p is just 1 over p. But we've got this constant n out the front, so that becomes n over p. Not too bad. So then we're going to differentiate again with respect to p to find the second derivative, dp squared. And in this case, how do we differentiate this? Well, just as a side note, we can rewrite this expression here just quickly. What I'm going to write here for you on this side is -1 minus p is 1 minus p to the -1, -1. So what we have to do is we have to bring the power down the front, so that would cancel out with the -1. Take 1 off the power, so to be 1 minus p to the -2, 1 off the power. But then we'd also have to multiply by the inner derivative, which is -1, so actually we'd end up with a -1 again. So, putting that all together, what we end up with is, when differentiated, we end up with -1 minus p squared. I equals 1 to n xi, and quite similarly, this expression here, you can think of that as n p to the -1 bring the power down the front, negative NP negative 2, and take 1 off the power when differentiated. We go from here to here, and so then that actually can be simplified down to negative N on P squared. So, now that we've found the first and second derivative, to find the MLE of P, which we will give the symbol P hat, we solve. Well, what are we going to solve? What we actually solve is that the first derivative of the log likelihood function with respect to P evaluated at the maximum likelihood estimate is equal to 0. And so what I'm going to do is I'm going to take our expression for the derivative, the first derivative. I'm going to copy that expression. I'm going to paste it here. And I'm going to equate that to 0, except we know that it is at the maximum likelihood estimate. So not just any value of P, it is in fact equal to at the maximum likelihood estimate is equal to 0. And now it's going to be the case that we're going to solve for this value of P. So the first step in solving for the value of P, I think, will be to take this to the other side of the equality. So in doing that, we end up with the next step, 1 over 1 minus P hat sum of I equals 1 to n xi is equal to n over P. Sorry, P hat. Then the next step in this equality, now let's think a little bit about this. I'm going to be a bit sneaky here. What I'm going to do is I'm going to get all the p's to one side. So I'm going to take this 1 minus p and multiply it up here. And I'm going to take this n and I'm going to divide it on this side. So I'd be left with something like 1 on n, I equals 1 to n xi is equal to 1 minus p hat over p hat. And you'll see why this was a little bit sneaky now. Not necessarily sneaky, but a bit clever. Now, I know what this expression here is. This is the expression for the mean. So I'm going to rewrite that as x bar n. That is the expression for the mean of n random variables. So I can write this expression as 1 over p hat here, 1 over p hat minus, you see that's p hat over p hat minus 1. And then what I will recognize is that I can in fact add this 1 to the other side, so it becomes 1 plus xn on this side, and then flip both sides. And so this leaves me with p hat is equal to 1 on 1 plus xn bar. So we're almost done here. We've found an expression for the maximum likelihood estimate. Now we just have to prove that it is in fact the maximum likelihood estimate. So to prove that L of P, the likelihood function, or in fact the log likelihood function, is maximized for P is equal to P hat, we have to show this property. We have to show, we have to show that the second derivative with respect to the log likelihood function, second derivative of the log likelihood function with respect to P evaluated at the maximum likelihood estimate is less than 0. Now note, now I'm going to get the expression that we found up here above for the second derivative, and I'm going to copy and paste that, copy that, bring it all the way down here. And what I'm going to do is I'm going to notice here that I've got this negative at the front here. What I'm going to do is, and I've got a negative out the front here, I'm going to take the negative out as a common factor so that I'm left with negative plus. So plus here, and it's all negatives, or it's a negative at the front. What I want you to notice is that this expression here, 1 over 1 minus p squared, well, 1 minus p squared is definitely positive, which means 1 over 1 minus p squared is positive. Now, xi, remember, xi can only take values, or it's an element of 0, 1, 2, and so on and so forth, which means the sum of xi's, at the very minimum, could be all 0. So this expression here has to be at least greater than 0. And this expression here, well, n is definitely at least greater than 1, and p is definitely at least greater than 1. Sorry, not greater than 1, but greater than 0. So this p squared is definitely greater than 0, which means this expression here is greater than 0. So everything here is greater than 0, which means this sum, multiplication of things greater than 0 plus something greater than 0 is all greater than 0. But now we've got a negative out the front, which means the whole thing together must be less than 0. And this is true for all values of p. So irrespective of the value of p that we have, that this is in fact true for all values. And so what this proves is that definitely at the maximum likelihood estimate, whatever it happens to be, this is also less than 0. And so therefore we have proven that, and so the MLE of P is in fact P hat, which we found to be 1 over 1 plus xn bar. And you notice now I use the capital xn bar to denote that it's a random variable. And that concludes our video for the derivation of the maximum likelihood estimate for the p parameter of the geometric distribution.